So today, so before we continue what we were doing last time about VC dimension, so there are a few things I wanted to mention yesterday, which I forgot to mention. So the first thing is something called the infinite removal lemma. So we proved, or we gave a sketch of the proof of the induced removal lemma last time. Now you can ask, can we do this instead of having one forbidden graph? Can we have multiple forbidden graphs? And it turns out that we can, and in fact, we can have even infinitely many forbidden graphs. So this was proved by Lior and Shapira in 2008, maybe. And the statement is the following. So for every graph family H, so this can be infinite. And for every epsilon, there exist two parameters. So there is delta, and there is an integer such that if G is epsilon far from being induced H3, then there exists some H in H. There exists some forbidden subgraph with at most n vertices such that G has at least delta n to the v of H used copies of H. Okay, so it's an analog of the previous statement, but now instead of just having one forbidden induced subgraph, we can have a family and even an infinite family. Then so one of the questions here there may be questions for which H do we have that delta, say 1 over delta, and M are binomial in 1 over epsilon. Right, so for which forbidden subgraph families is the dependence polynomial? This is a general question, it's very much open. So let me tell you a bit about, so let's consider just the special case H equals H. So this is just the usual induced removal lemma. So what is known here? So some things are known. So this is work by Lior and Shapira. And then there was a follow-up work of Lior and Fox. So two things. So first of all, if H is one of the following graphs, so I'll use PK to denote the path with K vertices. Right, so P2 is just an edge. So for this, 5 graphs, the dependence is polynomial. So first of all, observe that because we're talking about induced subgraphs, the problem for H and H complement is equivalent. You can always go to the complement. Right, so some of these cases are trivial. So this is an edge. This, you can think it's really a trivial statement. This is this path. Now, if a graph doesn't have this path, then the graph is a disjoint union of cliques. So those graphs are very simple. So you can imagine that you can somehow just by hand prove the removal lemma. And usually when you do these things by hand, it turns out to be polynomial. There's no regularity lemma involved. So this is more complicated, right? So graphs that don't contain this are called cographs. If you've seen it, so they also have a kind of a simple structural characterization, and you can use this. That's what Alon and Fox did. They used this structural characterization to prove polynomial removal. And on the other hand, for almost all graphs, it's not polynomial. So the induced case is not polynomial. So if H is not any of those graphs, and is also not C4 or the complement of C4, then it's not polynomial for the induced case. So you see that the only graph that for which we don't know this is C4. So this is open. What we do know, so we prove with Asaf Shapira, 2019. So we prove that the delta of C4 is at least 2 to the minus poly 1 over. So it's an exponential bound. So we don't know polynomial, but at least we know it's not tower. Like it's better than the tower type bound. The conjecture is that it is polynomial. Questions for this? Okay, so let me remind you where we stopped last time. So we proved this lemma that if G has BC dimension D, then for every epsilon, there exists some small number of vertices such that for any other vertex, there is some I such that the neighborhood of X is very close to the neighborhood of Xi. Okay, so this we proved last time, and now we will use it to say that a graph with bounded VC dimension has some nice partition. So let me tell you what I mean. So here's the definition. So let's V1 up to Vt, let's say, be an equipartition of the vertices, then we call it something P. So P is called epsilon homogeneous if for all but epsilon t squared, the pairs I and j, it holds that the density of VIBJ is at most epsilon or is at least 1 minus epsilon. So this is quite a strong property. So we require that for almost all the pairs, the density is very close to 0 or very close to 1. So this is called epsilon homogeneous. Okay. So one thing to note is that this is a stronger assumption than regular. So if between two sets you have that the density is at most epsilon or at least 1 minus epsilon, then this implies that xy is regular. So it's not exactly maybe epsilon regular, but it's gamma regular. Or so you can work out exactly what it is. I think it works with gamma, which is like epsilon to the 1/3. It wouldn't matter really what it is, just that it depends on epsilon. In fact, it depends polynomial. So this is a stronger notion than regularity. So in particular, there is a small, in particular, this an epsilon homogeneous partition is regular. So it's gamma regular for some gamma. So we know that every graph has a regular partition, but it's not true that every graph has a small homogeneous partition, right? So for example, a random graph, you cannot expect to have anything like this. Okay, so the theorem that we'll prove is that if the VC dimension is bounded, then we do have such a partition. So this theorem is, as far as I know, is due to Lemmas and Szegedy, and independently along Fisher and Newman. Following. So if the VC dimension of G is D, then G has an epsilon homogeneous partition into only 1 over epsilon to all of the parts. So you see that bounded VC dimension is quite a strong property. So it implies that there is a homogeneous epsilon homogeneous partition, and also that the number of parts is only polynomial in 1 over epsilon. So let's prove this. So we will use that lemma. So let x1 up to xt be given by the lemma. Now we need to apply the lemma with a bit smaller parameter than epsilon if we want to get epsilon in the end. So with parameter, let's say gamma. Gamma will be some polynomial in epsilon. which we will fix later. Well, we'll see what the requirements on gamma are. Okay. So these vertices, they give us a clustering of the graph. So what do I mean? So for each I, let xi be the set of all vertices x, which are close to xi, right? So such that the neighborhood of x, symmetric difference with the neighborhood of xi, is at most gamma n. Now, the lemma guarantees that every vertex is like this for some I. So this is a partition. So we take it to be a partition. If a vertex belongs to several of these xi's, we just put them in one of the xi's. Okay. So what we will claim is that this partition x1 up to xt is epsilon homogeneous. Now, so why can we expect that this is so? So imagine that here I could put actually 0. So instead of gamma n, I would have no error. Right? So I have parts x1, x2, and so on, xt, such that two vertices here have exactly the same neighborhood. Right? So, but now if you look between two parts, so if this is an edge, then every other vertex also makes an edge with this vertex because they all have the same neighborhood. But then every other vertex also makes an edge with all of them. Right? Because those also have the same neighborhood. So if you have an edge, it's complete. And if you have a non-edge, then it's empty. So it's really a homogeneous. So really all the bipartite graphs are complete or empty. And we can expect that if we have some error here, then we'll just have some error here. Right? So instead of being complete or empty, it will have density close to 0. Okay, so we'll prove this. But before, so observe that this is not necessarily an equipartition. So the parts, these xi's don't have to be of the same size. So let's define what it means to be epsilon homogeneous if the parts are not the same size. So P, so if I have any partition is epsilon homogeneous if the sum over all ij such that the density of xi xj is bounded away from 0 and 1 of the so-called the weight of xi xj is at most epsilon x squared. Right, so the way for us to define epsilon homogeneous for a general partition, not into equal parts, is instead of counting how many pairs of parts satisfy this, right, this is kind of the bad outcome. So instead of counting how many pairs of parts satisfy the bad outcome, we weigh those pairs according to their weight. So the weight is xi times xj. And we want this weight, total weight, to be less than epsilon n squared. And if you think about it, if all of these sets have the same size, then it's exactly the same as saying that the number of these pairs is small. And another thing I want to stress is that this includes the case I equals j. So we allow I equals j in this sum. right? Because you can imagine that one of the parts xi maybe is very large, maybe it's half of the vertices, right? And so we need to have control over what happens there. So we want to say that this part is homogeneous with itself. So the density of this part is close to 0 or 1. Okay. So let's prove that xi, that this partition is indeed homogeneous according to this definition. Let's prove this claim. So the idea is to count triples x, y, x prime, y, such that y is in the symmetric difference of the neighborhoods of x and x prime, and x and x prime are in the same part, xi. So what do we want to count? We want to count pairs like triples like this. So this is x and x prime. This is y. And y is connected to one of them and not connected to the other one. Right? That's what it means that this is a symmetric difference. It can also be other way around, connected to x prime and not to x. And x prime, they come from the same part, xi. So why do we want to count such things? Well, we expect the count of these things to be small, right? Because we know that if x and x prime are in the same part, they have almost the same neighborhood. So the count will be small. On the other hand, we will show that if a partition is not homogeneous, then the count of these things is large. So this will show that the partition is homogeneous. Okay. So instead of counting, let's sample. So it's the same thing. So sample x and x prime and y uniformly at random, such that x and x prime are in the same part. So you can imagine that we sample x and y, and then given x, we sample something else in the part corresponding to x. We sample x prime. And let A be the event that y is in the neighborhood of x, a symmetric difference with the neighborhood of x prime. So we can show that A has small probability. Why? So condition on x and x prime, and say that x and x prime are in xi or some I, doesn't matter which I. We know that the symmetric difference of their neighborhoods, so we can use the triangle inequality. So we know that both of them are close to xi, and therefore they're close to each other, right? So it's at most the difference of x with xi plus the difference of x prime with xi. And each of these things is at most gamma n, so this is at most 2 gamma n. So this means that the probability of A is at most 2 gamma. Okay, so this is one part of the argument. The other part, so the other part, so we will show if x1 up to xt is not epsilon homogeneous, then the probability of A is at least, so what we'll get is it's at least omega of epsilon squared. So we'll prove it, but given those two things, we see that we need to choose gamma. So we choose gamma such that gamma is much smaller than epsilon squared. And this will be enough. Okay, so let's prove this. So to prove this, we first need the following claim. So for vertex sets U and V, if the density of U and V is far from epsilon and 1 minus epsilon, sorry, it's far from 0 or 1, so it's between epsilon and 1 minus epsilon, then there are at least omega of epsilon. Let me do this with. Yeah, that's fine. Then there are omega of epsilon U squared V triples. Let me write it. Easier to follow. Then one of the following. So either there are at least omega of epsilon U squared V triples x prime in U and y in V with y in the symmetric difference of the neighborhoods, or the same thing holds with the roles of U and V switch. So this is kind of a simple claim, so let me explain to you what's true. So it's claiming that if we have two sets, U and V, and the density is not very close to 0 and not very close to 1, then we can find many triples like this, or we can find many triples like this, or we can find in the other direction. So many triples like this. we can't really commit on which direction we will get, because it can be that the graph looks like this, so we split this in half, and here everything is connected, and here everything is not connected, and then in one of the directions it doesn't work, right? So if I take two vertices here, then they have exactly the same neighborhood there. But in one of the directions it works. So here's a proof sketch. So there exists. So I'll just give you a sketch and you can fill out the details. It's pretty simple. So there are omega of epsilon, u squared, v squared, a four tuples, call them A, B, C, D. Let's call them U1, U2, V1, V2, such that U1, V1 is an edge, and U2, V2 is a node. So I'm claiming that we can choose we have many choices of an edge and then a non-edge. Right, so this is just because the density is bounded away from 0. So just choose an edge and choose a non-edge, the number of ways to do this. And now consider this pair. So case one, in at least half of them, let's say, let's assume that at least half of them, this is a non-edge. Okay, so either in half of them it's an edge or in half of them it's a non-edge. Let's say it's a non-edge. V1, U2 is not an edge. But then you can take x equals U1 and x prime equals U2 and y equals V1. So this is good for us, right? So this looks like that. But we are overcounting, right? So we have this count. Right, this is the count we have of the four tuples, but of course, now we want to count triples, and we are overcounting by a factor of v, because this vertex v2, we can choose it in any way to get the same triple. Right, so this gives least, so whatever we had there, omega of epsilon u squared v squared, we have to divide by v. Triples. And then case two is similar. So if this is an edge, then you can take these three vertices instead. Questions? Okay, so we proved this claim, and now let's use it. So remember that our general goal is to show that if this partition is not epsilon homogeneous, then the probability of A, we want to lower bound the probability of A. So let's do this. So Okay, so let's do this. So fix fix a ij such that, say I not equal to j, such that x, the density of xi and xj is between epsilon and 1 minus epsilon. So without loss of generality, so by this claim, without loss of generality, there are omega of epsilon, xi squared, xj, triples, x prime in xi, and y in xj, such that y is in the symmetric difference of x and of the neighborhoods of x and x prime. Okay, so the probability. So remember that now we choose this x and x prime and y randomly. So the probability that x, right, so the probability that y is in the neighborhood of x, symmetric difference, neighborhood of x prime, is at least epsilon times xi squared xj. And now what's the probability that, so we fix such a triple, what's the probability that will fall on such a triple? We have to choose x, which is n options. So the probability that x falls on where we want is 1 over n, and the same for y. But now for x, because x prime goes to the same part as x, then the probability is 1 over xi. Right, so this xi cancels, so we have omega of epsilon xi xj over n squared. Okay, so what is the probability of A? So this is true for any xi xj with density far from 0 or 1. So I can sum over all of them. So I sum over all ij such that the density of xi xj is between epsilon and 1 minus epsilon. And here I have just copy this expression. Now, if I assume that the partition is not epsilon homogeneous, then the sum of these weights is at least epsilon by definition, right? So this whole thing is omega of epsilon squared. Okay. So this proves our claim, and it implies that if we choose gamma small enough, so if we choose gamma much smaller than epsilon squared, then the partition is epsilon homogeneous. Questions?
The VC dimension version is small fraction of inhomogeneous pair is also undefinable.
Yeah. So for example, so there's this example. Maybe there are many examples, but this is a simple one. So you can take a half graph. So that means you have vertices x1 up to xn, let's say, and y1 up to yn. And xi is connected to yj if and only if I is bigger than j. X1 has no neighbors, x2 has this neighbor, x3 has those two neighbors, so on. So this has bounded DC dimension. It doesn't have an induced matching of size 2. Right, because somehow, because what happens here is that the neighborhoods are nested. So the neighborhood of x1 is contained in the neighborhood of x2, and so up to the neighborhood of xn. But here the neighborhoods are not nested. So it has bounded DC dimension, but you can check that somehow, no matter what you do, so somehow the best thing you can do if you want a homogeneous partition, at least intuitively, is to just split into intervals. So, and this interval with this interval would be empty, this interval with this would be complete, but the same interval with itself, you still have the half graph. So somehow you can show that you cannot avoid this. More questions?
Sorry, can you explain this probability again?
Yes.
I don't get.
So we see that between xi and xj, for each pair xi xj where the density is between epsilon and 1 minus epsilon, there are this many triples, which are bad. Right? So if our vertices, if x prime, and y fall on this triple, then A happens.
Yes.
Right? So the probability of A happening, and that for this xi and xj, is this number of triples divided by the probability of falling onto such a triple. And this probability, so suppose, so you have xi and xj. Suppose we fix a triple, and we want x to be here, x prime to be here, and y and like to be this vertex, and y to be this vertex. So what's the probability of this? The probability that x is this vertex is exactly 1 over n, because x is completely uniformly random. And same for y, it's 1 over n. But now the way we choose x prime is that after choosing x, we choose x prime in the same part as x. So the probability that x prime equals this vertex is 1 over xi. Because x prime is chosen from xi. So we get this probability, right? So this is the probability that x prime, and y equal a triple like this between xi and xj.
So do you need to add a condition on this probability?
Yeah, you mean when I write here? Yeah. So yeah, you're right. So let's say and x prime in xi, y in xj.
No, I see.
Okay, thanks. Yeah. More questions? Okay, so there is one small thing I'm hiding, and this is that in the statement, in this statement that we're proving, we want an equipartition. I didn't say it, but I can say it. We want an equipartition, and which is epsilon homogeneous, and at the moment it's not an equipartition. So the last thing we should do, so for the proof, is that we're going to split to make it an equipartition by dividing each by kind of refining the partition. So let me just say, so this kind of a technical step. I don't want to go into it. It's not difficult. It's just technical. So the last step is refine x1, xp to get an equipartition. So this is also a little bit of cheating because you cannot really refine it. So what you can do, so suppose this is the partition. So you can decide on the size that you want. So choose some size of sets M. And then just break each xi into sets of size M. But of course, you might have the leftover size less than M. And then what you can do, just collect all the leftovers and partition them into sets of size M. So the union of the leftovers will be small if you choose M small enough. And so the main part of the main, so almost all of the vertices will belong to this sets of size M that we get here. And the main observation that we can use is that if the density of, let's say, xij is less than epsilon, then every for every, let me write it explicitly. So for every equipartition, let's say u1 up to us of xi, and v1 up to vs of xj, all but square root epsilon s squared pairs ui vj have density less than square root epsilon. Right, so this is my claim. So if you have a pair of sets where the density is less than epsilon and you refine it, so if here you have density less than epsilon and you refine it, you take equipartitions, then doesn't matter how you do it, most of these pairs will have density less than square root epsilon. And the proof of this is Markov's. Right, so this is it's just Markov's. So you can think about the random variable is the density, and you know the average of the densities is just the density of the whole thing. So by Markov, the probability that you are more than square root epsilon is at most square root epsilon. I hope that made sense. Okay, so there is this refinement step, which is again, it's just technical, not very difficult. And then we really get an equipartition. Okay, so now we proved, let me see. So we proved this theorem. This theorem here. So we can use it to prove removal lemma, but we need a strengthening of it. And Alon, Fisher, and Newman actually proved the stronger form. So let me tell you the stronger form. So what they proved, so for every bipartite H, and and epsilon, there exists some delta, which is polynomial in epsilon, such that if G has at most delta n to the v of h bi-induced copies of h, then G has epsilon homogeneous equipartition of size at most 1 over delta. So what is the difference between, so can someone tell me the difference between this theorem and this theorem? So why is it a strengthening of this theorem? Right, so here we assume VC dimension is bounded. That means that there is some h such that we have 0 bi-induced copies of h, so no copies whatsoever. But here we allow some copies, right? So the conclusion is the same. So the conclusion is that we have an epsilon homogeneous equipartition of polynomial size, but the condition here is weaker. So we allow some copies, some bi-induced copies.
So I have a question.
Yes.
So this bi-induced looks natural because you look at the neighborhoods, right, of the vertex.
Okay.
Have people consider, let's say, tri-induced and look at higher order shattering of pairs?
Higher order shattering. So what do you mean? Tri-induced, you mean you have?
There are 3 parts, right? Then you don't care about inside. You only put
Right.
a restriction on crossing edges. Now, if you look at the link of a vertex, it gives you pairs on the other 2, and you can define some shattering for pairs also.
So people looked, so not in graphs, but in 3 uniform hypergraphs. So I'm not sure in graphs. I would have to think about the natural thing. But people do look in 3 uniform hypergraphs, and there are some recent results. So basically, the analog would be that you forbid some tri-induced thing as in a 3 uniform hypergraph. And the conclusion there, you can still prove that there is a homogeneous partition, but not of the vertices. You have to partition the pairs. So this is this kind of hypergraph regularity that I hope I get to touch on this tomorrow. But so it's true, but it's not true for vertex partitions. What is true is that you can partition the pairs such that the hypergraph sits homogeneously on the pairs. And another thing which is true is that if what you forbid looks like this, so this is your forbidden tri-induced thing, where one of the parts has one vertex and the others you do whatever you want, then it is true that you have a vertex partition, homogeneous vertex. So this means you forbid. This means that the links have bounded VC dimension. So the link of this vertex. So if this is true, then you have homogeneous. Okay, thanks. So let me continue a bit. So this theorem is very good for proving removal lemmas for forbidden bi-induced thing, right? So because either you have many bi-induced copies and then you're done, you're happy, like the conclusion of the removal lemma holds, or you have only few of them, but then you have a homogeneous partition, and once you have a homogeneous partition, proving like there is this machinery that we saw proving removal lemmas. So then it just works. So the last thing I want to do before stating the result I just said is that there is a way of reformulating this condition of, instead of forbidding something as a bi-induced subgraph, we can forbid something, some other graphs as induced graphs. So let me explain exactly what this means. So here's a lemma. So let F1 be bipartite, F2 be co-bipartite. I'll explain what this means. And F3 be a split graph. So bipartite, you know. Co-bipartite means complement of a bipartite graph. So this means complement bipartite. So in other words, this means that it's a union of two cliques. So the vertex set is A union B, and A, B are cliques. And the split graph is co-bipartite. Split graph, this means that the vertex set is A union B, and A is a clique, and B is an independent set. So you see that we have these three options here, so bipartite, co-bipartite, and split. And this covers all the ways to partition the vertex set into two homogeneous sets, so sets which are cliques or independent. And this is not a coincidence. We will see why we do this. Then, there exists a bipartite H, say with sides x and y, such that every pi-induced copy of H contains an induced copy of F1 or F2 or of one of these three graphs. So let me explain what this means and we'll prove it. So this is H. So we claim that there is some bipartite graph H. And such that, suppose we have a bi-induced copy of it. So that means that now someone comes and puts some edges inside these parts. And the claim is that no matter how they do it, we can find an induced copy of F1, F2, or F3. So let me give you just a sketch of this. Consider a bi-induced copy. Then use Ramsey to partition X into sets X0 and then X1 union XT, let's say, where X0 is small and X1 up to XT are, each of them is cliques or independent sets of size H, let's say, where H is the maximum. So we need to take it a bit large so that we can embed F1, F2, or F3. Let's just take it the maximum things. Right, so we can do it. So we have X, imagine X as a very large set. So someone comes and puts a graph here, and we can just apply Ramsey to find the one clicker independent set of size H, and then another one, and we can do this as long as we have many vertices. So at some point we have to stop, and this is X here. And same thing for Y. And so what we will do, so what is H, right? So we didn't say what H is. So actually we will choose H randomly. So now, so given any partition, so suppose that we have already a partition Xi and Yi. So I want to say that it's quite unlikely that I don't get any copy of F1, F2, or F3. Why is that? So suppose we consider some Xi and Yj. So each of them is homogeneous. So let's suppose that this is a clique maybe, and this is an independent set, but it doesn't matter. In either case, we're happy. So in this case, we want to get a copy of F3, right? Because F3 is the one that has a partition into clique and independent set. And there is some probability that the edges here are exactly right so that we get a copy of F3. Right, so the probability that no induced F1, F2, F3, well, the probability that the edges are exactly right is 2 to the minus h squared, right? Because I have h squared, or it's at least this, because I have h squared pairs, and if they're exactly right as I want them, then I get a copy of F3. Right, so the probability that this doesn't happen is this. Okay. And this has to happen for every pair, so for every Xi and Yj. So let's suppose that X and Y have size M. So how many pairs I have? So I have something like M over H squared. Right? Because I partition into sets of size H. Now I have some leftover, but this wouldn't really matter. So I have something like M over H squared. Right, so now I will just say that this beats the union bound over the partitions. Let me say this. Right, so this probability of failure. So if I continue from there, it's at most e to the minus m squared. And the constant depends on h. But h is given and we're allowed to choose m log. And the last thing we have to observe is the number of choices for the partitions, or xi, yi, is only m to the old m. Right? Because every vertex I have at most m options where which part to put it. So it's at most m to the m.
Why we need to account for these?
Because we don't know which graph we will get. So the setting is that we choose the random graph, between. Now someone comes and puts graphs on the sides.
We can reverse the order.
No, because we want to say that no matter how we put, no matter, so we only assume that we get a bi-induced copy of H. We don't know what happened inside.
I see.
So we're saying that no matter how someone puts these graphs, we get these partitions, and for all partitions this works. Right, so now we just have to observe that we can take the union bound because here we have m squared in the exponent, and here this is only like m log m, so the union bound works. So now let's combine everything. So what we get is the following theorem. So this appeared in a paper of Sasha Piran and myself. So let H be a finite graph family. So finite is important, which contains a bipartite, co-bipartite, and the split graph. Then the induced H removal lemma is polynomial. So this is, so in general, we don't know for which graph families it's polynomial. This is very, very much open. But for this special case, if we have a graph family which contains both a bipartite and a co-bipartite and a split graph, then it is polynomial. And essentially, I gave you already all the ingredients of the proof. Right, so there is this. So what you do is you take these three graphs here, so F1, F2, and F3, and you get this graph, bipartite graph H from this lemma, and then you apply that theorem to say that either you have many bi-induced copies of H, and then you're happy, or you have the homogeneous partition, and from the homogeneous partition you can prove them. Okay, so it was a bit quick, but we already covered essentially all ingredients of this. I think in the lecture notes there are a bit more details. Questions? Yes. Okay. Okay, so one thing let me mention, one case where you can apply this theorem is when H is consists of only the following graph. So the path with 4 vertices. So this graph is bipartite and co-bipartite and split. Well, you know it's bipartite, it's co-bipartite because you can partition it in this way, and it's split because you can partition it in this way. So you can apply it for, so I told you, I stated the theorem that for this graph, the induced removal lemma is polynomial. And there was kind of an ad hoc proof that used the structure of these graphs, but you can also just get. Okay. Last chance for questions before I move to a new topic. So, so next I want to talk about something that's called property testing. So what is property testing? First, let's look again at the infinite removal lemma. So it's this statement that's written here. And here is a reformulation of the statement. So this is also the infinite removal lemma, but this would be the sampling version. So here, so it says that for every graph family H, for every epsilon, there exists some integer q such that if G is epsilon far from induced H3, then a sample of Q vertices of G is not induced H3, with some large probability. So we can write, so let me write here 0.99, but you can make this probability as large as, like you can make this any constant close to 1 if you want. Okay, so let's go over the statement. So the assumption is the same. So you have some graph which is far from being induced H3. Now the conclusion is a bit different. So what we do now, we take a sample of Q vertices from the graph. So we just sample 1, 2, 3. So just sample vertices one at a time until we sample Q of them. And the conclusion is that with high probability, so let's say 0.99, then this sample is not induced H3. Okay, so let's explain why this statement follows from this statement. So in fact, they're equivalent. Let me just prove that this implies that, and you can think why the other direction. It's also true. So sample, so a sample of M vertices contains an induced copy of H with probability at least delta. Right, so if we go back to this statement, we see what is this statement saying, that we have this delta and M, and we have this graph H, which is of size at most M, such that we have at least, so we have at least this number of copies of it. So this means that if we sample, V of H vertices, or even more, so let's say M vertices, the probability that we catch a copy of H is at least delta. Now we want bigger probability, so let's just repeat this, let's say 1 over delta times, right? So repeat this, let's say 100 over delta times. Or let's say big C, right? So let's take a constant. And then the success probability tends to 1 as C tends to infinity. Right? Because the probability that we fail is most 1 minus delta to C over delta, because we have to fail at each attempt, and this is at most e to the minus. So if you take C large enough, you get success probability 0.99. Okay. Now, this is related to property testing. So now I can tell you what property testing is. Definition. So a tester for a graph property P is a randomized algorithm. So as you will see, there isn't that much algorithms here. Actually, it's really combinatorics, but a priori, it's a randomized algorithm that so it's given input. It's given an input graph, input G, and it's given some approximation parameter epsilon. What it does is samples some Q of epsilon vertices of G, and then it makes a decision. So it either accepts G or rejects G. And it satisfies such that. So if G has the property, then the tester accepts with probability. So here again, you can put any constant that you want, but let's say 0.99. And if G is epsilon far from P, then the tester rejects with probability 0.99. So I think the best example, like the simplest example of this and the best way to think about it is think about an election poly. So suppose there is an election and you want to get some estimate of what's going on. So here is a question that you cannot solve using a poll. So suppose you have some party and you want to know if this party gets more than 40% of the votes or less than 40%. Now, this you cannot do with a poll. Why? Because maybe just one vote changes it to under 40 to over 40, right? From under 40 to over 40. And you have no chance that, when you sample, you distinguish between these two possibilities. On the other hand, here's a problem that you can solve. Suppose that you want to know if it's under 40 or more than 41. So once you allow this gap, then you can do it, right? Then you can show that if you sample, then by any concentration inequality like Chernoff, this will work. But you have to allow yourself this kind of error gap. And this is exactly what we do here, right? So we have some property and we want to know if the graph is satisfying the property. So imagine the property is like triangle freeness or being bipartite or anything you want to know about the graph. If the graph satisfies the property, you want to recognize this with high probability. And if the graph is far from the property, you also want to recognize this with high probability. But if it's in between, so it doesn't have the property, but it's close to it, then you don't care about the outcome. Okay, question on the definition? Okay, so actually, this theorem that we have here, actually it implies a tester for many, many properties. So for any property which is of the form induced H free. So let's see why it is true. So let me just have one more definition. So P, and the graph property is hereditary if and only if P is closed under removing vertices. Okay, and observe that hereditary, that to be a hereditary property is the same as being of the form induced H3 for some, so for some graph family H. So it's exactly the same thing. So for example, you can take H to be all the H which are not in P. And then you can check that. So if you have a hereditary property and you take H to be this, not in P, then so it's kind of a tautology. You can think about it for a second. So that G satisfies the property if and only if it's induced H3 for this family. You can also take H to be minimal, not in. This is nice, and so you forbid fewer things. Okay, so what we actually showed is that, or what follows from this theorem is that every hereditary property is testable the proof. So what's the algorithm, right? So the algorithm is extremely simple. So here is the algorithm. So sample Q vertices and just accept if and only if the sample satisfies the property. So why does this make sense? So again, we think of a hereditary property. It means that the property is defined by forbidden induced subgraphs. So if the graph satisfies the property, right? If it satisfies the property, then every subgraph also satisfies it. It's hereditary. So with probability 1, the tester will accept. Now, the interesting direction is this one, but this direction follows from the removal lemma. So it's exactly so the correctness of the algorithm is exactly the statement of the removal lemma. Right? Because if the graph is epsilon far from the property, then this theorem guarantees that a sample of sufficient size will not satisfy the property with high probability. So this is just equivalent to this removal lemma. Okay. So what I want to do tomorrow is to talk about testing two specific properties. Because I think there are some nice ideas in these proofs. So I'll talk about testing bipartiteness. So of course, bipartiteness is hereditary, but we will do it with a polynomial number of queries, samples. So we will show that we can do it with a polynomial number of samples. And actually, the way this field of property testing developed is the first paper was by Goldreich Goldwasser and Ron in 1998. So they were the first to study this model of property testing, and they were interested in some specific graph properties for which they could prove this polynomial, this kind of nice polynomial algorithms. So one of the things they were doing is k-colorability. And so the first case is two-colorability, so by tightness, and I'll show you their proof. And the second thing that we will do is the property P of containing an independent set of size at least some constant times n. So rho is a parameter. You can think about it as 1/10, so your favorite parameter, your favorite number. So the property is, does the graph contain an independent set of size at least rho times n? So this was also done in this paper. They showed you could test for this. So using a small sample, you can decide if the graph has this property or is far from it. But actually, so about 2 years ago, I think there was a new proof discovered for this by Blaze and Seth. And their proof uses the container method. So it's maybe surprising at first, maybe in hindsight, not surprising, that you can do it with the container method. And this is also kind of simple and nice proof, so I want to show you this also. Okay, so that's what we'll do tomorrow. Any questions?
So you specifically mentioned this induced vertices. What if it's not induced?
So non-induced is a special case of induced, right? Because if you forbid,
right, you just
you can forbid all the supergraphs, right? But but this was so the way it's, so first they proved it actually for non-induced, and then they proved it induced. More questions?